Consider the graph of a velocity function, v of t. And let's say, just for instance, that on the x-axis we would have time, and that would be in seconds, and the y-axis would be, I don't know, feet per second. So we might have a graph that shows something that as time passes it's getting faster, and then it slows down, and then it gets faster and slows down, so on and so forth. And it should make sense, right, that what we have here is a picture of velocity. And a question that could ask, though, is what does the space between the curve and the x-axis represent? And if you think about it in terms of area, if we tried to say, what would this be, this rectangle? And that rectangle is going to have units on it, and its units would come from the length times the width. So in this case, it would be the length, whose units are seconds, times the width, whose units are feet per second. And when you multiply those quantities together, you're left with just feet. Right? And what does that mean? And consider in the same way an acceleration graph, and on the x-axis you have time in seconds again, and on the y-axis you have feet per second square. And we could ask the same kind of question, what does the space in between represent? And if we thought about it as a simple shape like a rectangle, you would have seconds times seconds squared, and you're left with a quantity that's feet per second. That's a velocity. And so we want to consider for a moment what the area under a curve represents, right? Where it comes from. And so there's a couple different things that you need to consider, but notice just in terms of your relationship, what you know about derivatives and integrals, that if you took a position function, its derivative would equal a velocity function. So it ought to make some sense that if you were to integrate a velocity function, you would end up with a position function. And you know that if you had a velocity function, its derivative is an acceleration function. And so it ought to make some sense, just based on that fact alone, that if you were to integrate an acceleration function, you would end up with a velocity function. Right? And so what an integral is doing is also addressing this idea of area under a curve. It's doing it in a very simple way. So let's deal with a problem. F of x equals x squared, and we're only going to look from 0 to 2. Alright, so we know the graph's going to look something like this. At 2, the y value would be 4. Right? And so a question might arise, how much space is here? And that space can be tricky to come up with, but we could come up with it, at least in terms of approximations, in this way. Right, a rectangle is a relatively easy shape to use, and so I could have a rectangle that's going from this rectangle, and I could have a second rectangle, and the area of those rectangles together would be an estimate. Not a great estimate, because clearly it's an overestimate, but it would still be an estimate of what the area under the curve would be. And notice that in this case my rectangles are touching the curve at the right hand side. Now I could do something else to estimate this. Right, same curve. I could have rectangles that are oriented this way. So I could have a rectangle here, and then another rectangle maybe here. It's really small, and this is an underestimate because it's missing some space. And notice that's the left hand sides that are touching the curve at this point. And if I wanted to get even better, I could just increase my number of rectangles, right? And so I'm going to look at x squared plus 1 just to give myself a little room here. So this graph would look something like this. And at 1, we know the curve's value would be 2, and at 2, it would be at 5. And I could have even more rectangles. So I could have a rectangle at 1/2 and another one at 3/2. And I could approximate it with my rectangles touching on the left, being something like this. And I could do something where what I'm suggesting is that the area of this rectangle plus the area of that rectangle plus the area of this rectangle plus the area of this rectangle is an estimate for the total area under the curve. And you can see it would be an underestimate, but it would be better than just using 2 rectangles. And hopefully this thought experiment can work for you, that if we increase the number of rectangles, it would become even better and better and better as an estimate. Right? So if I wanted to know what the area under the curve is, a way to get at it would be to take the length times the width of a bunch of different rectangles and add them up. And this is a summation problem, right? Summation notation means I'm just adding things together, and I would be adding things of the form length times width, and I might be starting at a variety of things. And all this is just pointing to is how many different rectangles am I going to have, and started at 1 versus 4. But I'm adding up areas of rectangles. And then if 4 rectangles is better than 2, and 8 is better than 4, and 16 would be better than 8, then clearly it ought to be the case that if I had an infinite number of rectangles, it would be perfect. So here's the idea. Notice that in this case, if I broke up the function x squared plus 1 and I broke it up into rectangles at the half mark, that each of these rectangles would have the same width. Each width would be a half. And what's changing is their height. Right. And the height of all of my rectangles is in relation to the curve. So in this case, I have 4 rectangles, and their width is all 1/2, and their height is all defined by the curve x squared, or their length, x squared plus 1. So I have width times length, and the 4 is just the number of rectangles. Well, as this process goes to infinity, right, if I broke this up into 8 rectangles, then naturally the width is even smaller. The width of each rectangle is now 1/4. The height, or the length of my rectangles, is x squared plus 1. There's 8 of them, and that's going to be a better approximation. And as I keep going with this idea, the width, right, as I get an infinite number of rectangles, the width of my rectangles gets really small. And my height stays the same. Right? I mean, that's the idea. Number of rectangles, width is now really small, height is still calculated in the same way. And it's from this that you develop the idea of integral. This is really just, I'm adding up a bunch of things, an infinite number of things, whose height is calculated at x squared plus 1, and whose width is infinitesimally small. Dx represents the width, it's infinitely small. X squared plus 1 represents the length, and if I'm integrating from, say, 0 to 2, I'm counting up the area of all of the rectangles from 0 to 2. And since their width is infinitely small, there's going to be an infinite number of them. And that's how I would find the area under the curve. Right, that's the idea behind the area problem.